A nuke is a kind of radioactivity. It's based on a kind of radioactivity. If you look on the chart, you find there are these two elements that are particularly interesting. One of them is called uranium. It's found in nature. There it is. Element number 92. So that means it has 92 electrons. Uranium has this, again, think of a flea or a mosquito in the midst of Memorial Stadium. And there's the nucleus. And it has 92 protons. It's uranium-238. What that means with 238, that's called the atomic weight. Now, all the weight is in the neutrons and in the protons. But if you subtract 92 from this, you find 6 and then 4, 146 neutrons. It has that many protons, that many neutrons. The neutrons have no electric charge, but they serve as a glue. At the same time, you put too many of them in there, or you don't put them in the right place, and the nucleus can become radioactive. This is radioactive. Uranium-238 is radioactive with a half-life of, actually I forget, it's billions of years. I do remember uranium-235. Let's look at uranium-235. What's the difference? It's still uranium. That means it still has 92 electrons. It's still uranium. That means it still has 92 protons. These little mosquito-like things in the center that have all of the mass. A proton weighs about 2,000 times as much as an electron. So an electron is there. It does have some mass, but it's really tiny. 92 protons. But it has 3 fewer neutrons. That's 143 neutrons. Turns out uranium-235 is radioactive. It has a half-life of about 1 billion years. Go back to the beginning of the solar system, and there was lots of this stuff. It was abundant. And then it started decaying. After 1 billion years, there was only 1/2 as much. After another billion years, only half of that. After another billion years, only half of that. After another billion years, only half of that. And here we are. And so it turns out that uranium-235 is about 0.7% of your ordinary uranium, just because it's mostly decayed away. This is decayed away too, but it has a longer half-life, so not much of it is gone. Other things have shorter half-lives, and they've gone even faster. Now, there's something very special about uranium-235, and there's one other. So this is called an isotope. Basically, it's uranium. It has the same number of electrons, so the same chemistry. If you want to do chemistry with uranium, it doesn't matter which one you have. They behave the same way. One weighs a little bit more, but you hardly notice that. In chemistry, the weight doesn't matter that much. It's mostly the electrons. So these are called different isotopes. And we can say, here's one isotope of uranium, here's another. This one is a rare isotope, not really rare, 0.7%. That's not tiny rare. It's enough there so you can do something with it. Then there's another element. This is one called plutonium. It's over here. It's done in light colors. That's because it doesn't exist naturally. Plutonium-239 is a very interesting one. There's another one, plutonium-238, which is actually harder to make. This one has a half-life of 24,000 years. Plutonium-238, which has one less neutron, has a property that its half-life is 80 years. Not only that, but its radioactive decay is alpha particles. Alpha particles are really nice. See, they don't even get through your skin as long as you don't breathe them in. Why? Because it decays so rapidly that it has lots of energy. It heats it up, gets very hot. You can turn that heat with something called a thermocouple into electricity. So the power, you're way away in Pluto. It takes 10 years to get there. This stuff will still be producing a couple hundred watts of electricity so it can broadcast things back. Really nice for space. But these are the famous ones, uranium-235 and plutonium-239. This has a half-life of about 1 billion years. But they both share a property that is key to the rest of this lecture. And that's the following. Suppose you have a neutron coming from somewhere. You can make a neutron. There are several ways to make a neutron. One favorite way is to take something that's radioactive and produce alpha particles. So we have a bunch here of atoms. You have a little bit of polonium-210 or something like this. It's radioactive, and alphas come out. Now you put a little beryllium next to it, and it turns out that when an alpha particle hits a beryllium nucleus, a neutron shoots out. So boom, out comes a neutron. This is a way of making neutrons. It's actually a very convenient way, and you'll see one of the atomic bomb designs I will show you has a little thing in the middle to make neutrons to make the bomb work. And all it does is it takes the alpha particles and a little beryllium, and they're sitting there happy as it can be. The alphas are coming out. They don't go very far. Then you bring these things together, and suddenly the alphas hit the beryllium, out come neutrons. You're not making them. You're releasing them from the nucleus. The alpha particle bangs into the beryllium, and out comes a neutron. If that neutron comes to uranium and hits the nucleus, it could stick to the nucleus. Certain probability it will stick. If it does that, we no longer have uranium-235. We have uranium-236. Now, here's the key feature of uranium-236. It becomes highly radioactive. Its half-life, the number is probably less than a billionth of a second. And it doesn't just give off an alpha particle. It explodes with something called fission. The nucleus breaks into two pieces, and they go flying apart. They're repelling each other. Once it breaks, once that nuclear force is broken by that extra neutron going in just the wrong place, the two sides break apart. We get these two pieces flying out. The pieces that come flying out are called fission fragments. Now, you take any nucleus and break it up into two random pieces, and the odds are those fission fragments will be radioactive. And in fact, most fission fragments are radioactive. That's called the nuclear debris or the nuclear waste. But anyway, a neutron comes in here. It doesn't smash it apart. This thing is almost coming apart anyway. It's held together by the nuclear forces. That neutron comes in there and just unbalances those nuclear forces in such a way that this thing flies apart immediately into two pieces. The pieces are different sizes. The stuff that comes out, because it's random pieces of nuclear material. Remember, in the early solar system, almost everything was radioactive because they were just random pieces of junk. Of course, the stuff that's radioactive isn't here anymore. So mostly we're left with either things that aren't radioactive, like ordinary carbon, or things that are radioactive with really long half-lives, like potassium-40. But if you just break up a nucleus, the pieces are probably radioactive, and most of them are, and this stuff is bad. It leads to two things. One is nuclear fallout. The other is nuclear waste. So these are two issues that are going to be coming up over and over again in these lectures. But that's where they come from. Plutonium, the same way. What happens is if a neutron hits this, by the way, it's not easy to get a neutron to hit the nucleus. Think of it. It's like shooting a bullet into Memorial Stadium and trying to hit that mosquito. Most of the time you miss. But when you do hit, the mosquito breaks up, releases enormous energy, and you get two fission fragments. Fission fragments, radioactive debris, that's very dangerous. Leads to nuclear waste and nuclear fallout. Now, here's the discovery that makes this thing suddenly exciting, fearsome, dangerous, useful. Not only do you get two fission fragments coming about, but on average from the uranium, you get two neutrons coming out too. Plutonium, you get three neutrons coming out on average. When this was discovered, it was seen as the key to the chain reaction. A chain reaction is, well, you got this thing, and you send one neutron in, you can get the neutron from beryllium. This thing fissions, out come two neutrons. Suppose you put enough uranium around here. Well, you have to put a lot because it misses most of the nuclei, right? So if I just have one next to it, it'll probably miss. It's like hitting a mosquito in Memorial Stadium. So you put more and more and more and more, and you put enough of them in there so that it's likely to hit. If you do that, that's called a critical mass. A critical mass is when you put enough material there that it's likely to hit. And you see, the word critical mass actually depends on lots of things. I mean, suppose you have a critical mass and it looks like this. It's not a critical mass anymore because the neutrons will fly out and they're not going to hit anything. So it's not just a matter of the mass. You have to kind of put it into a sphere to really make it into a critical mass so that there's no way you can fly out without hitting something. Can't have it long and thin. The geometry matters. There's another thing. Suppose you compress it and take the same thing and push it into a small, tight bundle. Well, think of the atoms. Here you are in the middle, and you're looking out, and you see the stars. Those are the other atoms. You wonder, if I go off in that direction, will I hit one? If you compress them and bring them really close and tight, the space between them is much smaller, you're more likely to hit it. So the critical mass depends on whether you've compressed it or not. So when we say the critical mass of something, you have to recognize it's not just so many kilograms. It's also the geometry. The first atomic bomb on Hiroshima worked in the following way. Two pieces, I don't actually know what the shape of the pieces was, but let's just assume it's a hemisphere like this. Each piece was less than a critical mass. What that means is on the average, a neutron would come out. It might hit. It might not. But on the average, you know, it would go. I mean, it would leak out. This was put inside of a gun. It's called a gun design. An ordinary explosive, not gunpowder, but probably something called a high explosive was put in here. This was dropped. It's called a gun design. They had two bombs. They had two bombs, and only two bombs. At the time they dropped this. Dropped down on a parachute. Once it was above the city, I'm not sure 1,000 feet or just how above, they detonated it in the air. They did that because this does maximum damage. This way you have line of sight to more. If you do it down the ground, you don't get as much damage as if you do it in the air. They figured out the most damaging altitude to do it. The way it worked was they detonated the high explosive. This piece went flying towards this piece. When they came together, you had a critical mass. At that point, you had two pieces that when a neutron came, now this neutron goes and causes a fission. Out come two neutrons. Each one of those causes a fission, 2, 4. And now you ask, how many times do you have to double? You go from 1 to 2 to 4, 8, 16, 32, 64, 128, 256, 512. After 10 additional steps, you're up 1,000. 10 steps later, you have another factor of 1,000 in the number of neutrons. You have 1,000,000. That's another 10 steps. Another 10 steps, you have 1,000,000,000. Another 10 steps, you have 1,000,000,000,000. By the time you get up to about 75 steps, you have Avogadro's number. That means basically every nucleus in that uranium has fissioned and released its energy. The energy being 1,000,000 times greater than an equal weight of TNT. So there's your atomic bomb. That's how it works. Use this doubling. Now, of course, there is a problem. Once this thing, what's happening is that when you get the fission, these fission fragments are flying out. And they have a lot of energy. It's kinetic energy. They collide into things and they heat everything up. So what you're really doing is turning this into heat. What the atomic bomb is really doing is taking that nuclear energy and creating a huge amount of heat. Now here we're going, 1 billionth of a second, 2 billionths of a second, 3 billionths of a second. These things are probably doubling every 10 billionths of a second. They double, 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 double. You get to a certain point where now you have the same energy density as dynamite. At that point, the thing blows itself apart. And it stops. Well, that's no good. That's like dynamite. You could have dropped dynamite. So what's the secret? The secret is that the neutrons are going really, really fast. You get up to the level of dynamite, this stuff is all heated, it's starting to blow itself apart, and here it goes, it blows itself apart. But meanwhile, the neutrons are going real fast, they're doubling, 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 and before it blows itself apart, you release even more energy. So that's the trick of the atomic bomb. It's one of the tricks, is you use these fast, super fast neutrons. So the doubling takes place a lot faster than the blowing itself apart. Finally, it gets up, where all the energy is released, and at that point you wait around for the thing to blow itself apart. And what do you get? Well, you get several things. One is you get that enormous energy of the blast. That's largely heat, and the heat goes to this big explosion. That's what killed most of the people. Estimates of from 50 to 150,000 people died in Hiroshima. We don't really know the answer because there wasn't that much left. So it's mostly this huge energy release. Now, in addition, some of these fission fragments are radioactive. Plus, there's some radiation emitted. There are gamma rays that are emitted from this explosion. Also, some of the neutrons leak out, and these neutrons can also hurt people. The death from radiation and from radioactivity at Hiroshima was really quite small. Mostly it was the blast. You can't die of cancer if you're killed in a fireball. So that's what happened at Hiroshima. A few days later, over in Nagasaki, another bomb was dropped. It was not a uranium bomb. The hard part of the uranium bomb is getting the uranium. That's hard. Plutonium is different. Plutonium, it turned out, requires a much more sophisticated design. I talk about this a bit in the text. I may come back to it in a later lecture. But a plutonium bomb requires that you take that material and you compress it. The reason has to do with some pollutants that they could not easily get rid of in plutonium. Plutonium-240, it turns out, tends to pre-detonate the bomb. It makes it go off before it's completely assembled. So it turns out the compression is necessary. Here's what you need to know. What I want you to know is that a plutonium bomb requires an implosion. What that means is, you can make an implosion work with a uranium bomb too. Let me show you a design of an implosion bomb. Here's a nice design of an implosion bomb. Let me put this up there. If we could put on this, this thing. And a couple of interesting features about this bomb. It's round, of course. And the roundness is what you do for an implosion. What you want, an implosion means you surround this thing with explosives. So when the explosives go out, they also push this thing in and compress it. That's called an implosion. Very hard to do. Try squeezing a water balloon, you see the problem. You squeeze it here, it comes out between your fingers. So the implosion has to be exceedingly uniform. Very difficult to do. This is a somewhat sophisticated advanced design. Uses what are called explosive lenses. We'll talk more about lenses when we get to optics. But basically the idea is you trigger off, see there are 32 detonators. So you have to fire them all off simultaneously. That's hard to do. So you get these detonators to all go off at the same time. They begin causing an explosion that goes inward now. But with these shapes, these things that are called the lenses, what you do is you make the explosion go in just such a way that it comes to get together into a perfect sphere just as it's coming in. So these were the two bombs. The problem with making a plutonium bomb is making the implosion work. I want you to know that. That's the difficulty. That's very hard. That's very high tech. And it's a high tech that you don't just get in the typical engineering school. This is a thing where you get really good people, you put them together, they do lots of experiments, they do lots of chemistry and lots of physics, and they figure out how to make it work. And it's not easy, but it was done by a group of scientists in 1945. It was done independently in Russia, in France. It's not, if you have the resources and a few $1 billion, you can do that. Not easy for a terrorist group to do it. That's the problem with the plutonium bomb. There are two types of bombs. There's the plutonium bomb. Problem there is not getting the plutonium. Problem there is making the bomb out of it. Problem with the uranium bomb is getting the uranium. So let me say a few words about that. You start off with uranium, natural uranium, that you dig out of the ground. Natural uranium, it's actually quite abundant. In granite, it's typically a part per million of uranium. A part per million, how much is that? Well, if you have a cubic meter, a part per million is a cubic centimeter. That's a lot. How much do you need to make it? That's just from granite. But if you go to uranium ores, you find a lot more of it. How much do you need to make a bomb? 15 to 18 kilograms. Well, let's see. Density of uranium is about 15 to 18, something like that. So 15 to 18 kilograms would be 1 liter. 1 liter of uranium, like a quart of uranium will do it. Plutonium is smaller. A cup of plutonium will do it. A cup of plutonium. That's the critical mass. A cupful. That's because you get 3 neutrons out. So how do you get this uranium? As I said, it's not hard to get the uranium. You can do it from granite. Nobody bothers. You go to uranium ores. But then what you get is natural uranium, which is uranium-238. Uranium-238 is 99.3%. And then the uranium-235, which is mixed in with it, is 0.7%. How do you... Now, if you keep them mixed, it will not work. The reason it won't work is very important. When the chain reaction starts and these neutrons fly off, most of the neutrons will be grabbed by the uranium-238. And when they do that, you don't get the fission. Actually, what happens when a neutron hits uranium-238 is an interesting thing. It turns to uranium-239. Uranium-239 decays. And then it decays again, and you're left with plutonium. So, a neutron on uranium-238 gives you plutonium-239. There are a couple of decays that take place in the process, but that's what you get. This is how you get plutonium. You get plutonium by making it from uranium-238. So you start with natural uranium. If you can make the chain reaction going, you can manufacture plutonium. If you want a bomb, you manufacture plutonium and then you extract it. We'll talk about that. That's called reprocessing. If you want to extract the uranium-235, it's hard to do. What I'd like to do right now is move on quickly to nuclear reactors. So what is a nuclear reactor? Here's the way a nuclear reactor works. What you do is you take uranium and you take ordinary, natural uranium, unenriched uranium, and it doesn't work. It doesn't work because the uranium-238 absorbs the neutrons. But this is what they figured out. If you surround it with carbon and you put it in little pieces, so when a fission takes place, the 2 neutrons leave and they don't run into any uranium-238, because that would absorb them. That's bad. But they leak out into the carbon. Carbon, it turns out, doesn't absorb neutrons at all. The neutrons bounce off the carbon. The carbon picks up a little bit of energy. It heats up. And the neutrons lose energy, so the neutrons slow down. This carbon is called a moderator. And the purpose of the moderator is to slow the neutrons. Now, so these neutrons slow down after a bunch of bounces. And at some point, they will actually hit their uranium again. And what they had discovered is that slow neutrons are not absorbed on uranium-238. They're just a little bit. So if you slow down the neutrons with a moderator, you can still get a chain reaction. What they really wanted to do was not really get a double, 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 because this thing would blow up. What they really wanted to do was get, on average, one of the neutrons. So you want one, you get uranium-235 gives fission fragments, typically 2 fission fragments, plus 2 neutrons. One of those neutrons you want to hit another uranium-235. The other neutron you'd like to hit uranium-238, making plutonium. So this way, every fission leads to one more fission. So once this thing gets going, it just keeps on going at the same level. It doesn't get bigger, 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 and explode. That's what a nuclear reactor is. So a nuclear reactor it has a moderator. That's the real key. The moderator means you can work with unenriched uranium. It keeps on going. In the beginning, you set it up so that you produce double, 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 double until you get the level you want. And then you put in control rods that absorb neutrons that make this thing keep in a steady state. So here's a key thing to remember about the nuclear reactor. In a nuclear chain reaction in a reactor, you're not doubling anymore. You want to keep it going at a constant rate. You make this plutonium, and then every once in a while you pull these things out, and you separate out the plutonium. Okay? So So that's called reprocessing. You got to know this word. You'll see this in the news all the time. That separates the plutonium. Reprocessing. Reprocessing means you go into the reactor and you remove the plutonium. Now, what's the big deal about nuclear reactors? So let me talk about that now. Let's talk about reactor accidents. About what happened at Chernobyl. In order for something to go off like a nuclear explosion, you can't have the uranium-238. But wait a minute, you can if you have a moderator, right? So maybe this thing will explode like a nuclear bomb. No, this cannot explode for a nuclear bomb for the same reason it works with unenriched uranium. This is a tricky thing. Really wake up now and pay attention. Everybody. There's a key thing here. In order to work with reactor-grade uranium, only 3%, you have to have the moderator. Otherwise, the uranium-238 eats up all the neutrons. If you have a moderator, you have slow neutrons. That means the chain reaction is slow. It comes out, it wanders around, and then it finally finds another uranium. Boom, out comes two of them. One of them goes to plutonium, the other is wandering around. Finally, it's a slow thing because of the moderator. Because it's slow, suppose you start to overheat. This happened in Chernobyl. In Chernobyl, they had a graphite reactor, a very badly designed graphite reactor. It started to overheat. It had a positive temperature coefficient. Nothing like that would ever be made legal in any country that had any kind of oversight. Positive temperature coefficient means that when it gets hotter, it starts reacting faster. That's absolutely illegal in the United States and every other rational country, but it wasn't in the Soviet Union. So the reaction started going faster and faster. It still had the moderator, because without the moderator, it wouldn't work. But it got going so fast that it got up to the energy density of TNT. Now, at that point, in the atomic bomb, the reaction is going so fast, because it has fast neutrons, that before the thing can blow itself apart, the reaction doubles, and you've released all the energy of all the atoms before the thing can throw itself apart. In Chernobyl, once it got up to the density of TNT, the thing exploded, and we never got a nuclear explosion. You can't get a nuclear explosion. You can't get the factor of 1,000,000 if you have slow neutrons. But you need slow neutrons or the reactor won't work at all. So what happens in these things is the Chernobyl nuclear reactor blew up like as if it were loaded with TNT. There was an explosion, but not a nuclear explosion, not an atomic bomb type explosion, just a pure dynamite explosion. Well, what's so bad about that? Well, 36,000 people dead is what's the result of that. Why is that? Because it's not the explosion that killed people. What happened is the explosion set the graphite on fire. And the graphite started to burn. Now, what's the problem with that? What's the big deal about a fire? The problem is all these fission fragments that are in these pellets. They're highly radioactive. Those are the things you want to take out, and you'd like to remove the plutonium from them. You'd like to bury them underground somewhere, but instead they go up in the smoke. So this highly radioactive stuff is going up in the smoke. And that's what then spread over the city of Chernobyl and all the way up to Sweden. And when you calculate it, as I said, you'll never see these deaths because they're a tiny fraction of the other cancer deaths. But we calculate 36,000 real people, each one of whom is probably a nice person, and they're dead because of this. They would have lived longer. So it's a real tragedy, 36,000 real deaths. And it came about because of a reactor accident that ran away. It would never blow up like a nuclear bomb because it uses moderated neutrons. If the neutrons aren't moderated, then the chain reaction stops because then they're absorbed on the uranium-238. We can't have both. To make it work with slightly enriched uranium, reactor-grade uranium, you have to use slow neutrons. If you use slow neutrons, the thing can't explode. Well, it can explode a little bit, enough to set the thing on fire and spread this radioactivity. That's what happened. What do people worry about for the American reactor? You're not going to have a carbon fire. Probably you're not going to have a reactivity accident. Reactivity is when it starts getting hotter and it gets worse because it has a negative reactivity. If this thing overheats, it tends to slow down the nuclear reaction. So what do people worry about? They came up with what they call the worst case scenario. Worst case scenario. And the worst that anybody could come up with is a nuclear meltdown. And let me show you how the meltdown works. This is the idea. Somehow a pipe breaks and you develop a leak in the reactor. And this water all flows out. What's the first thing that happens when the water flows out? The chain reaction stops. Why does the chain reaction stop? Because there's no moderator. Without a moderator, the chain reaction. So the first thing that will happen in this worst case scenario is the chain reaction stopped. By the way, in the Chernobyl, once this thing had the explosion, the chain reaction stopped. Now, once the water is all drained, these things are full of radioactive particles. So what happens with them? Well, they're hot because they're radioactive. The water was cooling them. In fact, that radioactivity contributes to the heating of the water. This water is made hot, and that's what goes and runs the turbines, the hot water. The chain reaction is used to heat water. And the water runs a turbine. That's how a nuclear reactor works. So what happens when the water is all gone? You're left with the fuel. The fuel gets hot. It might melt. So they put in a very carefully designed emergency core cooling system. This is called the core cooling system. And that cools it off, so there's no problem. Well, if there's no problem, then this is not the worst case scenario. So therefore, let's assume the emergency core cooling system fails. After all, we're trying to get the worst case. What's the probability it will fail? Well, you can calculate that. It's infinitesimal. But, people make mistakes in these calculations. They don't realize things. So let's do the worst case scenario. By the way, I believe in the nuclear industry, that's the only industry in which we require a worst case scenario. You have to assume that everything fails and then ask what happens. The water's gone, the emergency core cooling system fails, this stuff just heats up. What happens when it heats up? Well, it will melt. So nothing's working, the stuff will melt, it'll dribble down and form a little puddle on the bottom. Now this stuff has rather thick steel. I forget exactly how thick it is. I think maybe a foot or two of steel. And it's inspected all the time to make sure there are no cracks and things. But worst case scenario, let's say this pool happens to accumulate in a nice small area and it melts its way through and dribbles out the bottom. What happens then? Well, this whole thing is surrounded by a concrete containment building made of reinforced concrete. I forget again exactly how thick that is. I used to know these numbers. But it's probably 8 feet thick or something like that. Chernobyl had no containment building. None. This has the steel, and then it has the concrete. So it gets to the bottom, it should spread out and cool off, but what if it doesn't spread out? What if it somehow manages, worst case scenario, to come down and work its way through the containment building? Gases can still escape. And there are some gases that can escape and lead to bad levels of radioactivity if that happens. So this is what people analyze. This is called the nuclear meltdown. This gas can escape and spread over the countryside, and it's a bad amount of radioactivity. Is it as much as Chernobyl? Oh, no, nowhere near as much as Chernobyl. Why not? Well, first of all, it's only the gases that get out. The rest gets into the ground. Oh, that might get into the groundwater. Yeah, but the difference between getting into the groundwater and having come and smoke and cover the city. So this worst case scenario is not nearly as bad as Chernobyl. The nuclear meltdown, once you've had this thing operating for a year or two, these things are full of radioactive fission fragments. The ones that decay right away, those are fine. They give you more heat. You use that heat to heat the water and run the reactor. But after a while, you're left with the things that live for 50, 80 years, something like strontium-90. And that's not decaying enough. And you've used up your uranium, so you pull out the rods and put in fresh uranium. You've used up most of the uranium, and the decay heat isn't doing you much good. So what do you have now? You have a rod that's full of plutonium and fission fragments. So what do you do with this? Well, many people, like in France, think the right thing to do is you take the plutonium and you separate it out. That's called reprocessing. That's removing the plutonium. And then the plutonium can also be used in a nuclear reactor. It's a fuel. You put plutonium in instead of uranium.